The, the next speaker is also online. Is Professor Ivan Araut, who is gonna tell us about symmetry arguments, solving time-important problems in physics.
Yes, thank you very much. Let me share the screen.
Yes, please.
You can see it?
Not yet.
What about now?
No, we don't see
No,
it.
you don't see it. Let me see. Share
Just
again.
see your face.
Here. What about now?
No.
No. Okay, let me.
Yeah,
I'm able to see your screen online, by the way.
Yeah, now it's okay, but please make it full screen.
Can you see it now?
Not full screen.
Okay. Now I know what happened. Full screen, you mean?
Yes.
1 second. Now okay?
No. Yeah, now it's okay. Yeah, you may start. So you have 13 minutes for talking and 2 minutes for questions, please.
Okay, thank you very much for this opportunity. My name is Ivan Arro. I am based at the University of St. Joseph in Macau, China. And since it's very short talk, I will just make a collage about several results which I obtained using symmetry arguments for solving some issues in physics. This is math. This is based on several publications I did in the last few years. So, of course, as we know, symmetry is the invariance of a system under some transformation, and the basic example is when we rotate a ball. This is an example of global symmetry. If it's local symmetry, we would deform locally the ball unless we introduce a gauge field, which restores the symmetry of the system. Symmetries could be finite, and there are several examples. This is the dihedral group, etc. Of course, every time there is a representation of the group, when you apply it to the action is invariant up to total derivative. Why symmetries are so important? Because symmetries govern interactions. Symmetries tell us which quantities are conserved. Symmetries explain the behavior of a system. Symmetries, when broken, give us information about phase transitions and general changes on the configuration of a system. The first result I will show is the results of dark energy, which I published in two papers in Modern Physics Letters and European Physical Journal C. In such a case, what I did is to correct the integration of the 0-point quantum fluctuations. Normally, when we integrate the vacuum energy density, we apply a triple integration, and we assume that the azimuthal angle is 2 pi. What I did is to use a symmetry constraint emerging from the de Sitter metric and impose it here in the superior limit. And using the uncertainty principle, I obtain the way how the vacuum energy density is supposed to scale. And this has a physical interpretation. It means that the ultraviolet modes, they cannot live long enough for covering enough phase space, while the infrared modes, they live long enough for covering the phase space. So that's why the ultraviolet modes don't contribute. This was one result. Now, jumping to another problem, which was dark matter. In that case, I decided to explore different vacuum solutions to the traditional ones. Normally, when we explore the solutions, we assume spherical symmetry, the standard R² solution here. I decided to explore these families where you can only scale by R with the purpose of taking the tangential velocity of the conserved quantity instead of the angular momentum. There are two publications around it, but those don't represent the real vacuum solution. The real vacuum solution is this one, and the potential which emerged is this one. And I proved that phenomenologically this potential reproduces satisfactorily Fisher and the scales of dark matter. So it's too premature to say that this is the solution to dark matter, of course, but it's a good advance. Still, we have to prove lensing and other issues related to cosmology like CMB and so on. Now let's jump to a spontaneous symmetry. Sorry, a spontaneous symmetry breaking is when the symmetry is preserved by the Lagrangian or the Hamiltonian, but is broken by the vacuum state. I think you are all familiar with that, and the most basic example is applying the force to this bar with such intensity. The force is one of the free parameters we can control. Other free parameters can be. And suddenly the force is high enough for deforming the bar, but the direction of the formation is arbitrarily. The same happens in systems where initially the ground state is at the center and stable, suddenly becomes unstable, and then any perturbation helps you to select the ground state. And this is a spontaneous symmetry breaking. When there is a spontaneous symmetry breaking, of course, there are broken generators, broken symmetries. The role of the broken symmetries is to map one vacuum to the next. This can be easily demonstrated. And also, there are some gapless particles emerging called Nambu-Goldstone bosons. One example of a spontaneous symmetry breaking is ferromagnetism. When you have arbitrarily oriented magnets in a material, if you decrease the temperature and you increase externally the magnetic field, which are the two free parameters you can control, there is a moment after which there is a phase transition below a critical temperature, such that any small perturbation, in this case the magnetic field, tells you what is the vacuum you select, what is the direction of the vacuum you select. This has plenty of applications in several fields. Now, a few years ago, of course, if you have an order parameter which with a non-zero vacuum expectation value, still if you do the superposition of all the possibilities of the other parameters, that gives you a zero. And this a few years ago gave me the chance to demonstrate that the Nambu-Goldstone theory emerges fundamentally from the quantum Yang-Baxter equations, which basically are triangular relations. And this is true as far as you take one of the lines as one Nambu-Goldstone boson, the other line as another Nambu-Goldstone bosons, which interact, and the third line is a fictitious particle represented in the generating vacuum. I could demonstrate that there is a correspondence between the double commutator, which, basically the other parameter can be expressed as a double commutator, and this can be seen in the papers, double commutator between the Lie algebra, the broken generators, and the Nambu-Goldstone field. And with that, you find a correspondence between each term and each triangle here. And that's how I demonstrated that. And I could solve in this way the dispersion relation problem, which is a problem in condensed matter physics where the Nambu-Goldstone bosons scale with the dispersion relation quadratic instead of linear, and the counting problem also, because of course there are cases where these two lines represent a single degree of freedom, and there are cases where they represent different degrees of freedom. This is the standard formulation of the Nambu-Goldstone theorem. You have a group and a subgroup which remains invariant, and of course the dimension of the coset normally in the standard situations represent the number of broken generators. Now I jump to Hawking radiation because this is another interesting result I obtained in the last years using symmetry arguments. I found a Lagrangian. This is generic. I think the Hawking radiation is a generic result, and you can formulate a Lagrangian in this way. This is the Lagrangian, such that if you find the Euler Lagrange equations, you obtain the Hawking radiation, basically the equation, which is supposed to be the black body spectrum, no? It has a potential of this form. This is the potential with three free parameters, actually, not two. But I could demonstrate that if you take the particle number operator as an order parameter, and this is possible because before the formation of the black hole, there is no particles, no? There is no particle creation, so it's zero. After the formation of the black hole, there is a non-zero particle number operator, so we can take the particle number operator as a order parameter. If we do that, this can be seen as a mechanism of spontaneous symmetry breaking. The symmetry under analysis, of course, is the symmetry under internal exchange of configurations. In this way, I could interpret the black hole evaporation process as a mechanism where the black hole is permanently trying to find an equilibrium condition without success. So it's always trying to go to a ground state, but becomes unstable, evaporate, it becomes stable again, and then unstable again. So it's a cycle which never ends.
Ivan, you have 4 minutes left.
Okay, sure. Yeah, I have my chronometer here. Now, in the symmetry arguments, of course, this is the symmetry argument of black holes. This is the fact that the particle number operator is an order parameter, because if you sum all the possible order parameters, it vanishes. Okay. Of course, it's non-zero if you evaluate in a single vacuum, but if you sum all the vacuums, it's zero. And this could be proven in the paper. But if this is true, it means that the black hole not only emits particles, also has to emit antiparticles in order to restore perhaps the information when it evaporates. This is still a research in process, of course. And finally, I want to jump to the neutrino, because I noticed the conference is mostly in neutrino physics. I also use symmetry arguments for analyzing the neutrino problem. Remember, the neutrino comes from the electroweak theory, where it's SU2 tensorial product U1, which is broken to U1 electromagnetic. But of course, I will not share so much details because it's a research in progress. But what I can say is that this matrix in principle is a rotation in some angles, but I interpret it in a different way, taking the each flavor of the neutrino as a vacuum state. And of course, there are some relations. So you take the flavors as an order parameter. This superposition has to vanish. And at the end, I found some constraints which more or less match with the experimental observation. And those constraints, I use also quantum Jahn-Baxter equations for putting each flavor of the neutrino in as a side of the triangle. And the angles here are 2 theta actually, which are the mixing angles. And of course, I could predict that that the hierarchy is normal hierarchy. In the case of, so it means that mass 3 is much larger than mass 1 and mass 2, which are supposed to be close to each other. And then now I didn't want to abuse on time, so these are the conclusions. The origin of the neutrino mass maybe will come from symmetry arguments. The quantum Jahn-Baxter equations have a correspondence with Nambu-Goldstone theory. This is an old result I obtained in 2019. The black hole information paradox might be solved through symmetry arguments. The first starting point is to realize that the black hole evaporation process is a process of a spontaneous symmetry breaking. The observed cosmological constants value is obtained via symmetry arguments. The symmetry constraints come from the background itself, and the angular momentum conservation. When you integrate the azimuthal angle, you find the corresponding constraint, which you have to put in the superior limit of the integration of the vacuum energy density. And finally, the effects of attributed to dark matter, in my case, at least emerge from deviations from spherical symmetry at astrophysical, at galactic scales. Of course, it's too premature to say that this is the solution, but I formulated the problem in this way. And every time there is a new vacuum solution in general relativity, we have to take it serious, because general relativity until now has not failed classically. Well, unless you take dark matter and dark energy as a failure. And that's my talk about my discussion about today. Thank you very much.
Thank you very much. Questions? Yeah. Just a moment.
You have proposed a certain relation between angles in the neutrino mixing matrix, but these parameters are in general scale dependent. And do you investigate if this relation is protected from the quantum corrections? Because it presumably should be valid at, say, unification scale, and quantum correction can break it at low energies.
You are talking about dark energy?
No, I'm talking about the relation between angles when you discuss the neutrino mixing matrix.
Neutrino, yeah,
Yes,
okay.
yes.
Yeah, sorry, I was thinking you were
You
talking about the
proposed a
angle.
certain relation,
Yeah.
this one, yes, and this relation maybe it really takes place for the observable values, but all these angles should depend on a scale, because the nature is described by quantum field theory, and all these values are running. And if this relation is protected from quantum corrections.
Well, that part I have to investigate because, of course, this is the earliest stage result, and it's not perfect because even if I obtain the angles near to the observational, it still is not exactly the same angles. No, there are some deviations. Perhaps those quantum corrections you mentioned will be able to improve this prediction. Let's see. But for the moment, what I did is just to find geometric relations imposing the constraints coming from these triangular relations, coming from Jan Baxter, taking the flavor of the neutrino as another parameter in order to impose the constraint that the superposition of the flavors vanishes. It's like evaluating in different vacuum states. And then some relations emerge. And those relations give me the capability to make predictions to N1 and 2 and 3. And theta, of course, I have to input something. Let's say, still I have to input one of the observations, at least I have to put with the hand, and then for predicting the others, no? So it still is too premature to say, but there are two preprints running right now in archive, yeah.
Okay, thank you.
So, are there any other questions online? Well, if not, let's thank the speaker again.
Thank you very much.
And the next speaker is Roman Nevzorov from FIAN, who is gonna tell us about generation of lepton asymmetry in the minimal composite Higgs